Welcome to Trigonometry on what you need to know to be prepared for this upcoming unit. So what I did is I selected some problems that hopefully you've been presented with that maybe you either forgot or maybe that it's just been a while since you have, worked on them to make sure we refine our skills. So therefore, when we get into the new material, you kind of have a little bit of that foundation built up. So what we're going to do is we're going to kind of review Pythagorean theorem. We're going to go back over these, actually just the three trigonometric functions, how they are related on a triangle. We're going to go back through special right triangles to help us evaluate missing sides. And then we're going to work on our simplifying with radicals. And we're really just kind of focus on just with radicals, just, simplifying a radical as well as simplifying when the radical is in the denominator. And that's really about it. This doesn't cover everything you need to know for trigonometry, but hopefully, some of these problems you've been presented with, or at least a part of them have been presented before. So therefore you can quickly kind of get caught up as we get prepared to get into trigonometry. So the first thing, Pythagorean theorem, we got to make sure, remember this, that's a big one. A lot of people, even, years after they leave high school or college, they remember the Pythagorean theorem, a squared plus b squared equals c squared. And typically because it's one that most people, most teachers had people memorize, and you just use it a lot. And in this chapter, we are going to be using Pythagorean theorem quite a bit. So, I don't even say you need to memorize it. It's just we're going to use it so often, you will automatically have it memorized. Now, the important thing, though, just to remember with the Pythagorean theorem is A, B, and C is very easy to remember, but sometimes this gets confusing with students when we're dealing with triangles that have variables of x's and y's or of expressions. So what I prefer to, also remember this is really it's leg squared or plus leg squared equals hypotenuse squared. So therefore, we need to remember what are the different parts of a triangle. Well, the two sides that make up a right triangle are what we call our legs. So we're going to call these two the legs. And then the side length, excuse me about the sneeze, the side length that is directly across from the 90-degree angle is what we call our hypotenuse. All right, so what you can see here is we have two legs, but we don't have the hypotenuse. So therefore, we could label them A, B, and C. Sometimes, sometimes that's helpful, but I think in this stage in the game, we can recognize that we have two legs, we need the hypotenuse. So therefore, that's going to be 3 squared plus 2 squared is going to equal, and we could call hypotenuse C squared. But don't get stuck on the hypotenuse has to be C. Like you can really label it any letter you want to, or, variable. So 3 squared is going to be represented as 9. Plus 2 squared is 4 is equal to c squared. 9 plus 4 is 13 equals c squared. Now we need to remember we still need to solve for c. So we're going to take the square root and we're going to be c equals the square root of 13. Now previously in other chapters we dealt with taking the positive and the negative version of that when we're introducing the square root, which is true, which is something we still need to remember. However, in this case, you can see that we're dealing with a measurement. So therefore, our measurement, having a negative hypotenuse doesn't make sense in the context of this problem. So since we're dealing with the quantity, we're only going to be dealing with a positive side length of an angle. However, there will be later problems where direction is going to be played into it. So that is something you need to kind of remember. So in this case, it doesn't make sense to have a negative hypotenuse, but in maybe a word problem or another problem, that may be the case. All right, so in the next example here, you can see that 7 is my hypotenuse, 5 is a leg, and then we have another missing leg. So I'm just going to call this A. You can call it anything you want to, but therefore I know that I have a squared plus my other side length, which is 5, which is going to be 5 squared, is equal to 7 squared. So therefore I have a squared plus 5 squared is 25, is equal to 49. Now I'm just going to go ahead and subtract my 25 here. And then I get a squared is equal to 24. Now in this case, it's a little bit interesting because in previous, we couldn't simplify the square root of 13, right? That was like it. Well, 24, when we go ahead and take the square root here on both sides, we can simplify the square root of 24. So what we're going to want to do, if you remember, is we want to break down 24 into a set of square numbers. And obviously, hopefully this is something that, we've kind of worked on, or at least you're broken down with, but I'll just kind of do one set. You want to find the largest square number that divides into 24. In this case, we could rewrite 24 as 4 times 6. Now I can separate that. Now I can separate the radical as square root of 4 times the square root of 6. Either way, I can break this up into the square root of 4, which is 2, times radical 6. So you can just kind of see that's how using the power rule to simplify that. All right, the last one here is, let's call this A, so let's call this B. Either way, guys, you know that that's a leg, so you're going to follow the same operation. So in this case, I'll have 4 squared plus my other leg, which is going to be B squared, is equal to 5 squared. And 4 squared is 16, plus B squared is equal to 25. Hopefully you recognize this as a Pythagorean triple, maybe. But either way, what's nice about this Pythagorean triple is that all the side lengths are even integers. And there's multiple different Pythagorean triples that we'll kind of get into throughout this chapter, but the 3, 4, 5 triangle is one of the more famous and most commonly used. All right, so that's kind of the basic Pythagorean theorem. That's some old stuff. Now let's kind of get into our trigonometric ratios. And if you remember, a lot of times sine, cosine, and tangent, a lot of people, don't really understand what they are. They are a function. So they have an input and they have an output. So we need to understand what exactly, what do they mean? What do they represent? Well, to kind of give you, again, just a quick little version, non-mathematical, they're just a comparison. They're just saying, with relationship to this angle, because it's always the sine of, the cosine of, the tangent of. So they're always taking the of is of an angle. All right, so this is saying the sine of x. So here's our angle x. So what the sine represents is the comparison of the opposite side compared to the hypotenuse. So basically we're saying, how big is the opposite side compared to the hypotenuse? The interesting thing to remember about right triangles is the hypotenuse is always the largest side, right? So therefore, the opposite side is never going to be as big as the hypotenuse. It's never going to be the same measure as the hypotenuse. So we know that we kind of have a range here of the sine it can, like, the largest the opposite side can be is really, really close to the length of the hypotenuse, and the smallest it can be is 0. So between 0 and the length of the hypotenuse, there's a whole bunch of ranges. And if it was the same length, that would be 1. So therefore, we're looking at a ratio between 0 and 1. And a lot of times these are represented as decimals as well as in fractions. So, another easy way to remember this is the SOHCAHTOA, which basically means sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. But again, what does the opposite over hypotenuse mean? Again, it's just a comparison. The sine of x is equal to 3 over 5. Yes, 3 over 5, but really what that is doing is, how big is 3 compared to 5? And if you wanted to convert this into decimal form, that's 0.6, right? So it's a little bit more than half as big, right? So 3 is a little bit more as half as big as the hypotenuse. That's kind of a way to internalize what exactly these trigonometric functions represent. So the cosine of x is then going to be the adjacent side compared to the hypotenuse, which in this case is 4 over 5. Now, my triangle is not drawn to scale, so please don't mark me on that. So, but again, this is kind of important here. You can see that the adjacent side is closer to the size of the hypotenuse. So you can see when we're comparing, as far as the adjacent and the opposite side compared to the hypotenuse, the adjacent side is bigger than the opposite side, right? It's a closer ratio of 1-to-1 ratio with the hypotenuse. So that's just how we kind of use these as a comparison of the side lengths for triangles. And then the tangent here of x is going to be the opposite side over the adjacent. Now, one thing I did not talk about is, if you remember, which side is the opposite, which side is the adjacent. That's really important. So we already know 5 is the hypotenuse, right? The adjacent side is the side that is going to be between your angle and the right angle. And the opposite side is going to be the side length that is opposite of your angle. Now, That's very important for A, B, and C for x, because that was the angle that we were referring to for sine, the sine of x. Now, if we do a trigonometric ratio for y, we notice that our angle has now changed. Now we're dealing with y. So now our adjacent side is 3, and our opposite side is going to be 4. So you can see that the ratios change based on which angle we are referring to. So now, if I'm looking for the sine of y, I'm looking for the opposite over hypotenuse, which is 4 over 5. If I'm looking at cosine, I'm looking at for the adjacent over hypotenuse, which is 3 over 5. And the tangent, which is going to be the opposite over the adjacent, which is 4 over 3. Okay, and hopefully you can kind of recognize some relationship here, the connections between sine, cosine, and tangent based on which angle you are referring to. All right, so now one of the things that I think most students definitely do not carry or remember from geometry is the special right triangles. And, in reality, why would you? It's not something that is very useful after kind of like geometry class or whatever chapter, you learn it, and you don't constantly utilize your special right triangles. But it is very helpful, especially when we want to find the missing sides of a triangle, to remember these relationships, as well as once we get into this unit, you're going to be able to see how these kind of work out. So, in our notes, we kind of go through, where these come from and so forth. In my case, basically what I want to do is we can just use Pythagorean theorem in this first one. Actually, no, let's not use it. Determine sides using special right triangle relationships. Okay, so I guess... Okay, yeah. So let's actually just kind of refer that we remember our special right triangle relationships, which most students do not. So the 45, 45, 90 triangle, that's a horrible 45, 45, 90 triangle, looks like this. Now, it doesn't matter what the angles, what the side lengths are. If this is x, the other leg has to be x. And if you were to do the Pythagorean theorem to figure this out, which we'll do in our notes, you get x to the square root of 2. Let's just use this relationship here for the 45, 45, 90 triangle to find the missing sides of the triangle. That's really the bulk what I want you to get practice on. So if I have 2 and I have 2, then to get the hypotenuse, rather than doing the Pythagorean theorem, which you could do, that's just going to be 2 square root of 2. Now, to go from a leg to the hypotenuse, I multiplied by the square root of 2. So if I have the hypotenuse and I want to go to the leg, that means I'm going to want to divide by the square root of 2. Now, just remember rationalizing the denominator, right? And that's something we're going to obviously do, but let's just get a little practice here. If I want to rationalize the denominator, what I need to do is get the radical off the denominator. To do that, I'm just going to multiply by the square root of 2 on the top and the bottom. Therefore, it gives me square root of 2 over 2. This is usually referred to as a more simplified form compared to 1 over square root of 2. All right, now let's go and look at the 30, 60, 90 triangle. So the 30, 60, 90 triangle is a little bit different. On the 30, 60, 90 triangle, let's say we have a short leg, and let's call that x. So that would be 60 degrees, and this would be 30 degrees. So it's important that, I didn't talk about this, that a 45, 45, 90 triangle is an isosceles triangle. That means you have opposite angles that are the same. You also have opposite sides that are the same. Well, that's not the same as a 30, 60, 90 triangle. It's not isosceles, it's not equilateral, it's a scaling triangle. So therefore, if you have x, the hypotenuse is 2x, and the length here is going to be x square root of 3. So here, you basically, when you're looking at the triangle, you want to identify, unless you have the hypotenuse, you want to identify, do you have the leg, the long leg, or the short leg? In this case, we have the short leg, so I have x. So therefore, the hypotenuse is just going to be double that, which is 6. And then go from the long leg, I'm just going to multiply by the square root of 3. And this is this relationship, this special relationship that we investigate in geometry. And again, we will investigate again in this chapter. So now on to the next one here, where I have a side length 8, the long side. So to go to my short side, now remember, to go from short to long, we multiply by the square root of 3. So to go from long to short, we're now going to need to divide by the square root of 3. And again, if I want to find the missing sides, let's just put this in simplified form. So let's rationalize the denominator here. So that'd be 8 square root of 3 over 3. I can't simplify this any further, right? But if I want to go from short leg to the hypotenuse, I'm just going to multiply by 2 here, which would give me a 16 square root of 3 over 3. So again, let's show my work here. Let's just show it, just so for people following along or checking my work, they can see where I got that. So I have 8 square root of 3 over 3. Okay, now on the last one, remember to go from short leg to long leg, I can multiply by 2. So if I have the hypotenuse, to go from short leg to hypotenuse, I multiply by 2. So if I have the hypotenuse and I want to go to the short leg, I'm going to divide by 2. So that would be 1/2. And then to go from the short leg to the long leg, I'm going to multiply by the square root of 3. Square root of 3 times 1 is square root of 3. So therefore, you're left with square root of 3 over 2. All right, now let's go ahead and get into just some practicing simplifying radicals. Obviously, we've already been exposed to having to simplify them in the front, in the back. So it is just something, though, that, in a lot of problems, having a radical simplified, or a simplified form is preferred. Getting the radical off the denominator is in many problems going to help us, have the problem, be able to simplify the problem further down the road. So obviously, just to kind of review, the square root of 9, what number multiplied by itself gives us 9? That answer is 3. When we have a number that is not a square number, we want to see if we can break it down into a product of a square number times another number. In this case, 8, 4 times 2. Therefore, using the rules of radicals, I can break this up into the square root of 4 times the square root of 2. Now I can take the square root of 4 separately, which is 2 times the square root of 2. Hopefully this is, again, something that you're not going to need to do every single time or do it this slowly. But, again, you can kind of see where we're coming from this. Another way is to kind of look at this is like the factor tree. If you really are having trouble with this, just remember you can break something down in like 4 times 5, 2 times 2. Because remember what I said, like a number multiplied by itself, square root of 3 times 3. Like what number multiplied by itself is going to equal 9. So in this case, you could rewrite this as 3 square root of 2 times 5. And what we did in this case, what we learned using this prime factorization is you break it all the way down to its prime numbers. And then since we're taking the square root, we're looking for pairs of numbers that multiply by itself. Now, again, we're going to take this out and notice we have the 3 in front of here. Now, notice that 3 is being multiplied by the square root. So where does this 2 go? Well, this is just going to go on the outside, but multiplication is still going to be the operation. It doesn't change like addition or subtraction or anything like that. Like look at here. When I took that 4 out, it became a 2, but it was 2 times the square root of 2. So now we have 3 times 2 times the square root of 5. And I can just multiply these numbers just like how they are, 6 times the square root of 5. All right, so now we're going to work on the rationalize the denominator. It doesn't really actually simplify the problem, but a lot of times it is helpful in the problems that we're going to be doing to not have a radical in the denominator, or at least it's considered by mathematicians and math people to be a more simplified solution. So in multiple choice problems and so forth, you might see you have the right answer, but the answer is not in the same form.
So if you have 6,
we just want to make sure
to go
that
from the short leg to long leg,
familiar
multiply by
and
the square root of 3.
know when
That means
to
you go from the long leg to the
utilize
short
this,
leg,
and
you're
when
going to divide
by the square root of 3.
So again,
To rationalize
go from the short leg to the
multiply
long
by the
leg, you're
square
going
root of 2 over the square root of 2.
multiply by 2.
And that's
So
going
that'd
to
be
be 12
12
over
the square
this
root of
2
3.
times
And
square root of 2
if I
times
wanted to
square root of 2
simplify
is the
this,
square root
I
of
would
4,
just
which is
multiply by the
just
square root of 3
2.
on top and bottom.
Now, one big mistake a lot of people do is they want to multiply, not really a mistake because there's
gives
nothing
me
wrong with
a
it,
square root of
but
3
they just want to
over
multiply everything in the denominator. On
Here,
the top
I
well,
could
you don't need to do
rationalize
that.
the
You can
denominator.
just multiply what's under the radical, because the whole
that would
goal
give me a 12
of
square root of
rationalizing the
3
denominator
over
is get
3,
rid of the radical in the
which would
denominator.
give me a
So we can't multiply a
4
number outside of a radical
square root
inside
of
of a
3.
radical, so the numerator remains the same.
So
And then
that would give
here
me
we
a
have 3 times
4 squared of 3.
Remember that becomes 2.
Let's do that.
So
that
3
would give
times 2
you
is 6.
yeah,
And then
4
notice
squared
how
of
we
3.
can simplify our solution here. So this becomes a negative square root of 2 over 3. So 2 over 6 reduces to 1/3. Now, in this next example, we're probably going to want to, we should look into simplifying our square root of 12 first. So if I square root of 12, I recognize that to be the square root of 4 times 3. So square root of 4 is then 2 times square root of 3. Notice here, this simplifies now to 3 over the square root of 3. So now the next one triangle here is if I have the long leg. So if I want to get to the short leg, I'm just going to divide by 2. And then to go from short leg to long leg, I'm going to multiply by the square root of 3. So that one is radical 3 over 3. The 3's divide out, and you can see we're just left with square root of 3. Right. So you can see how this one brings in multiple steps. That's why simplifying, I would say, would be very, very helpful to do kind of first. Now, what about when we have radicals in the numerator and the denominator? Well, you can simplify. You can write them under one radical, but not always is that going to be the best case. Like in this first one, there's nothing we can. So now the square root of 7/3 is not going to help us out at all. I'm just going to rationalize the denominator here. Now again, remember, since they're both under the same radical, which is index of 2, we can multiply them together. So that's going to give us the square root of 21 over 3. So you can't multiply a number outside of a radical, inside of a radical, but as long as they both are square roots or cube roots or, fourth roots, then you can multiply the radicands, the values under the radical. In this next one though, rather than rationalize the denominator, I just want to make sure you understand that the square root of 6 divided by the square root of 3 is the same thing as the square root of 6 divided by 3. Well, 6 divided by 3 is 2. So we can just answer that question rather easily. So just remember that you can, work with those rules of radicals to simplify the solution. And in the same case here, I'm going to break this up into 3 over 12. I know I can reduce 3 over 12 into 1/4. Now here it might not be as obvious, so therefore I'm going to break this back apart in the square root of 1 over the square root of 4. That allows me to see this as 1 over 2. So it might not have been as obvious, from there, but you can see that's really just 1/2. So as a quick little recap to prepare you for trigonometry, we covered simplifying radicals by rationalizing the denominator, as well as, just simplifying a number under a radical using prime factorization or the product rule of exponents. Then also we looked at using our special right triangles to find missing sides of an angle. We went back over our sine, cosine, and tangent, our trigonometric ratios of a right triangle. And then we we remind ourselves of the Pythagorean theorem. So again, guys, this is not an exhaustive list of everything you need to know for trigonometry, but I feel pretty comfortable that if you go through all these questions and feel confident in what we covered in this sheet, then you'll have the right foundation to do very, very well in this unit of trigonometry. So now it's time to get started. Best of luck. Cheers.